we already learned the one reaction of the haloarene with the metals. That is, there is the reactive metal which reacts with the haloarene, and there is formation of that of the, we learned at inverse synthesis, that is the fitting reaction we learned. In the fitting reaction, the haloarene reacts with that of the active metal and there is formation of the diphenyl. That reaction we learned. Now let us learn the nucleophilic substitution reactions of haloarenes. Now haloarenes also undergo the nucleophilic substitution reactions. But the reactions of haloarenes, that is nucleophilic substitution reactions, are very slow. Now why that are slow? Now these nucleophilic substitution reactions of haloarenes are also called as the acid reactions. Now haloarenes means aryl halides. That means the halogen atom is directly attached to that of the benzene ring. So they are called as the haloarenes or aryl halides. Now they show very slow. They show very low reactivity or slow reactions towards nucleophilic substitution reaction. They show very low reactivity towards nucleophilic substitution reaction. Now what is the reason why haloarenes or alkyl halide show low reactivity towards nucleophilic substitution reaction? Now there are the two main reasons. That is, first is the resonance effect. Now in a haloarene, the halogen atom directly introduce one of the lone pair on that halogen atom into the benzene ring, and there is the stabilization of that molecule due to the 5 different resonating structure. In 11th standard, we learn about the resonance effect, how the resonance effect is shown by the curve arrow, and how the different resonating structures can be drawn. Now all these we learn in the 11th standard. Now second, that is the reason for the low reactivity of haloarenes toward the nucleophilic substitution reaction is the sp hydride state of carbon atom. Now the carbon atom in the benzene ring, there are the 6 carbon atom in the benzene ring. Now any carbon is sp2 hybridized because there is alternate single and double bond into the benzene ring. So the carbon atoms are sp2 hybridized. That is one of the reason why the haloarene or alkyl halide show the low reactivity toward the nucleophilic substitution reaction. Now let us learn the first, that is the resonance effect. Now one of the lone pair, I already told you that one of the lone pair of electrons on halogen atom, every halogen atom have the 3 lone pairs of electrons on that, and one is get used for the formation of bond. Now one of the lone pair of electrons on the halogen atom is always in conjugation with the pi electrons. You know that conjugation, alternate single and double bond is called as the conjugation. What is conjugation? Conjugation means alternate single and double bond. Now one of the lone pair present on that halogen is always in a conjugation with the pi electrons of the ring. The ring have the 3 pairs of pi electrons. And for example, chlorobenzene show following resonating structure. Now see the resonating structure I drawn on that of the blackboard. Now there are the 5 resonating structure we can draw of this chlorobenzene, and due to that chlorobenzene is very stable molecule, and as it is stable, it show the low reactivity. As it is stable, it show the low reactivity towards the, that is the nucleophilic substitution reaction. Now this is the first resonating structure here. Now what is there? Now see, on the chlorine there are the 3 pairs of the lone pair of electrons. Now these 1, 2 and 3. Now out of that, this one lone pair is always in the conjugation with that of the pi electron. Now these are the 3 pairs of pi electron of the ring. Now this goes here. At the same time, this must go to on that carbon, because carbon have only 4 bonds around it. Now this carbon atom, see here 1, 2, 3, 4 bonds are already there. But if these electrons comes here, then there is the formation of double bond. And due to that double bond, what happens? There may be the 5 bonds will be there. But that is not correct, because one of the pi electron must shift on this carbon. Now this we will learn in the 11th standard. Now here, as this lone pair passes towards here double bond, this lone pair of the pi electron comes here. Now there is the positive charge on the chlorine. Why? Because the electrons shift here. So there is the positive charge. Now in the second resonating structure, what happened? These electron can come here, and at the time these shift here. Now see, here is the negative charge and there is the double bond. And this chlorine is as it is. This chlorine have the positive charge. And these 2 lone pairs are also as it is. Now this negative charge again when goes here, this passes here. See in the third structure. Now here is the negative charge now. Again in the fourth structure, what happened? This goes here and this double bond comes here. There is the negative charge here now. And here is the double bond will be formed. Again in the next structure, what happened? This negative charge come here and this goes on its original position, and there is such type of at the end of the first structure, like structure, that is the fifth structure. Now in this way, students, what happened here? Here, due to the 5 different resonating structures, this chlorobenzene molecule is very stable, and they have very low reactivity toward the nucleophilic substitution. That means they do not easily undergo nucleophilic substitution reaction. That is the point. Now what is here? Resonant structure second, third, fourth show double bond character to the carbon fluorine. Now see here, in the second structure, in the third structure and in the fourth structure, between the carbon and chlorine there is the double bond character. And thus carbon-chlorine bond in chlorobenzene is stronger. We know in the 11th standard, as the multiplicity of the bond increases, the bond becomes stronger and stronger. What is mean by multiplicity? That is single bond, double bond and triple bond. Triple bond is always stronger than the double bond, and double bond is always stronger than the single bond. So as in this 3 structure, second, third and fourth, there are the double bond character between the carbon and chlorine. So carbon and chlorine bond becomes very stronger and shorter. That means easily that chlorine cannot be replaced because the bond is stronger. So what is the reason? Thus chlorine carbon bond in chlorobenzene is stronger and shorter than the chloroalkane. Now what happened in the chloroalkane or alkyl chloride? There is no double bond. Alternately, as in the ring in this haloarenes, in the chloroalkane what is there? There is no double bond. So the carbon chlorine bond in alkyl chloride or chloroalkane is always weaker than the carbon chlorine bond in the haloarenes, because there is the double bond character between these 3, second, third and fourth structure. Between the carbon and chlorine, there is the double bond character. Due to that, it becomes shorter and stronger. But that is not same point into the alkyl or aliphatic alkane. That is the, we call that is the chloroalkane. Into that chloroalkane, such double bond character between the carbon chlorine bond is not there, because there is the no conjugation, no resonance. So shorter than the chloroalkane molecule, this bond, carbon chlorine bond is shorter than the carbon chlorine bond into the chloroalkane, such as in methyl chloride or ethyl chloride. In this way, the CCl bond length in chlorobenzene is only 169 picometers. See here, but as compared to the CCl bond 178 picometer. This is larger. In the alkyl chloride, the CCl bond length is larger, but in the aryl chlorides, the CCl bond length is shorter, and due to that, the carbon chloride bond do not break easily, and there is the nucleophilic substitution reactions have the low reactivity. Now this is the first region. Now let us study the second region, that is the sp2 hybridized state in the of the carbon in the benzene. What is that? And these two regions, they always ask into the examination why the haloarenes or aryl chloride show low reactivity towards nucleophilic substitution reaction. Then you must explain these 2 points. One point we already explained. Now let us learn the second point. That is the sp2 hybridized state of carbon atom. Now first take the screenshot. Now we are learning about the nucleophilic substitution reactions of haloarenes. Now in that I already told you that if the conjugation increases or resonating structure increases, the chlorobenzene or haloarene molecule becomes more unreactive towards the nucleophilic substitution reaction, because already the haloarenes are very low reactive towards the nucleophilic substitution reaction, and due to that of the sp2 hybridized carbon atom and CCl double bond character in second, third and fourth resonating structure, what is that? The CCl bond becomes more stronger and stronger, and it is very difficult to break that bond. So hence it is difficult to break the CCl bond in the haloarenes, and they show the low reactivity towards the nucleophilic substitution reaction, SN reactions. Now, but these haloarenes, due to the presence of electron withdrawing groups, you know that electron withdrawing group into the A1 standard, that groups having the minus I effect. Which are that groups? All halogens have the that is the minus I effect. Again the NO2 group, cyanide group, that is the carboxylic group. All these are the electron withdrawing group. If such groups are present at the ortho and para position of that the benzene ring in haloarenes, due to that what happened? The reactivity of the haloarenes increases, because they withdraw the lone pairs into the ring. Now see what is there? But the presence of electron withdrawing group at ortho or para position greatly increases. Greatly means very, that is the maximum rate. Greatly increases the reactivity of the haloarenes towards the SN reaction. Now greater the number of electron withdrawing groups, see this is very important sentence. Greater the number of electron withdrawing groups at the ortho and para position, greater is the reactivity of these haloarenes towards that of the nucleophilic substitution reaction. So, if there are the more number of electron withdrawing group at the ortho and para position of the benzene ring, that show the more reactivity towards the nucleophilic substitution reaction. This is very important. Now, but electron withdrawing group at meta position has no practically effect on the reactivity. Though there is the electron withdrawing group, but if it is present on the meta position, then there is no so much effect on the reactivity of these haloarenes toward the nucleophilic substitution reaction. Students, we are learning how these haloarenes behave towards the nucleophilic substitution reaction. Already they show the low reactivity, but if there is the presence of electron withdrawing group on the ortho and para position, then increases the reactivity of these haloarenes towards the nucleophilic substitution reaction. But if the electron withdrawing groups such as the nitro groups etc. are present on the meta position, there is no effect on the reactivity of these haloarenes toward the nucleophilic substitution reaction. Now we are learning here the three reaction. Into that, as the electron withdrawing groups on the ortho and para position increases, how the reactivity of that haloarene increases. Let us learn into these three reactions that are present on the blackboard. See that three reaction. I here draw that three reaction. Now first one is that the reaction of this para-nitrobenzene. Now there is only one electron withdrawing group at the para position of these haloarenes. Now what is happened due to this electron withdrawing group? Somewhat the reactivity increases. Suppose there is only the chlorobenzene will be there. Then if chlorobenzene reacts with these, that is there is the reaction of this chlorobenzene with that of the aqueous alkali. Definitely there is formation of as in the haloarenes, in the alkyl halides there is formation of alcohol. So in the haloarenes there is the formation of phenol. Definitely phenol. That means these chloride get replaced by the OH group. But if this NO2 is not there and only chlorobenzene will be there, what happens? It requires more time for that reaction. But if we attach this electron withdrawing group at the para position, what happens? These reactions somewhat quickly happen than the reaction of only the chlorobenzene. So electron withdrawing group effects such that the reaction rate increases, the reaction increases very fastly, the reactivity of that haloarenes increases due to that the electron withdrawing group, especially at the para and ortho positions. Now there is the as the chloride get replaced by this OH group and there is the para-nitrophenol. Now this the strong alkali NaOH in the presence of temperature 433 Kelvin and this is the aqueous solution, so water is definitely there. Now see the second reaction into that the two electron withdrawing groups are now there. Now as the electron withdrawing groups increases at the ortho and para position, reactivity definitely increases. So instead of such strong alkali, mild alkali such as sodium carbonate can also form the phenols. There is no requirement of the strong alkali now because the reactivity increased by these two, that is the ortho and para electron withdrawing groups on that of the ring. So very mild alkali such as sodium carbonate can also react and there is formation of this phenol. And the name of that phenol is, now how the numbering is given? The numbering is given in this way from this position 1, 2, 3, 4. Suppose they give the number 1 position to that of the chlorine. Yes, chlorine 1, 2, 3, 4, 5 and 6. Now see here, this is the definitely chlorobenzene, but there on the second and fourth position there are the nitro groups. So 2,4-nitro-chlorobenzene is the reactant, and if this mild alkali in the water solution or aqueous solution form the phenol, this chlorine get replaced by the OH group and there is very requirement of mild alkali. Why? Because electron withdrawing groups are present at ortho and para position, the reactivity increases and there is formation of, now this is also phenol 1, 2, 3, 4, 5, 6. Now if the nitro groups are not there, it is the phenol. But at the second and fourth position, there are the 2 nitro groups, so it is the 2,4-dinitrophenol. Now if the again one of the nitro group, that is the electron withdrawing group increased, now we know that there are the 2 ortho position and 1 para position. We not attach the nitro group at the meta position, remember that. Because meta position do not have electron withdrawing group are present on the meta position, there is no effect, practically no effect on the reactivity. So only the ortho and para position, there are the electron withdrawing group. And so it is the, now as giving numbering 1, 2, 3, 4, 5, 6. This is 2, 4, 6 trinitro-chlorobenzene. And it requires no alkali because its reactivity so much increases due to the 3 electron withdrawing group. So only warm water can replace this chlorine and there is Chlorine is replaced by the OH group. Only warm water. There is no such alkali required for the reaction because it is very reactive due to the 3 electron withdrawing group, 2 on the ortho position, 1 on the para position, and there is formation of this 2, 4, 1, 2, 3, 4, 5, 6. Now 2, 4, 6 triNitrophenol is obtained. Such is the effect of student. That is the presence of the electron withdrawing group on the ortho and para position of the benzene ring towards the nucleophilic substitution reaction. As the groups increases, electron withdrawing group increases, reactivity increases. Remember that. Now this is about the nucleophilic substitution reactions of the haloarene and how they affect their reactivity we learn. So if student you understand this video, you can like, subscribe and share so that the maximum students can write their answer confidently, because give reason is definitely there why the haloarenes are low reactive toward the nucleophilic substitution reaction and why the electron withdrawing group increases the reactivity of the haloarenes toward the nucleophilic substitution reaction. Such type of question will be there. You must write this answer into that and give all these 3 reactions so as you can there put your answer very confidently. So take the screenshot and write down the notes in your notebook in a beautiful handwriting. Thank you.